We have a 70 kilogram skier that's gliding at 2 meters per second when he starts down a very slippery 50 meter long 10-degree slope. We want to know what his speed is at the bottom. So what we're being told is the mass of the skier. He's initially going at 2 meters per second, so that would be his initial velocity. And he goes down a very slippery slope. Very slippery means that we can neglect friction. We imagine the skier is going through snow, so he would slide pretty easily. And we're told that he slides for 50 meters. That is his displacement. And we're told that it's a 10-degree slope. So that would be the angle of inclination of our slope. So here, if we want to know what is his speed at the bottom, we'll find that via change in kinetic energy. We're going to look at what work is being done on the skier, and then we'll be able to find his speed via kinetic energy. So we have our 10-degree slope, we have our skier, he's got his little ski poles with him, and we know that he is going to go 50 meters. But he's not going 50 meters in a straight line. In fact, his displacement vector is 50 meters in this downward direction, downward along this inclined plane. The reason that he's sliding down is that he has gravity acting on him, and gravity is acting straight down. In this case, gravity is the force that's being applied. His displacement is along the slope, and we're interested in the angle between the force and the displacement. If this is 10 degrees and this is 90 degrees, that means that this angle here has to be 80 degrees. And so we can say the work done on our skier is the force that's acting on him, in this case is gravity, times his displacement, times the cosine of the angle between the two. In this case, it's mg times his distance times the cosine of that angle. And the work comes out to be just about 6,000 joules of work is done on our skier by gravity as he goes down the slope. This work is going to be an increase in his kinetic energy. We've said that work, external work in this case, which is gravity acting on him, is a change in kinetic energy, which is a kinetic energy final minus a kinetic energy initial. What we've seen thus far is the kinetic energy initial has been 0 when an object has been motionless to begin with. In this case, he has an initial velocity, so he has a non-zero kinetic energy. Basically, he's moving, and as he goes down the slope, gravity is going to work on him, and he's going to move faster at the end than he was at the beginning. But what we can do is say that his kinetic energy at the end would be his kinetic energy at the beginning plus the external work that was done on him, in this case by gravity. His initial kinetic energy was 1/2 times his mass times his initial velocity of 2 meters per second plus the external work done on him by gravity. And we see that his kinetic energy at the end is a little bit over 6,000 newtons, and his kinetic energy at the end is expressed as 1/2 mv squared. And so we can gather from that his velocity at the end is 13.1975, we'll say, because we're interested in significant figures. And so we'll go ahead and round that and say that his final velocity is actually 13 meters per second. And so we see that we want to hold on to all of our figures all the way through, and then only to truncate our significant figures at the very end.